Right, we're going to talk about the rational root theorem. Well, first, what is a rational root? What is a root? If you have x squared minus 4, the roots of x squared minus 4 are x equals 2 and x equals minus 2, because those two numbers, 2 and minus 2, make this 0. When x is 2, not sometimes it's 2 and sometimes it's negative 2. If x is 2, that is, if we had x squared plus 3x plus 4, you can put 2 in here and minus 2 here. Whatever value you pick for x, whether it's 2 or minus 2, you have to be consistent throughout that problem, that verification. If you square 2, you get 4. You take away 4, you get 0. X equals 2 works. What about negative 2? Whenever I see x, I put negative 2. Negative 2 squared is 4. Take away 4, yeah, 4 take away 4 is 0. So those are the roots. Now, what are rational roots? Well, those are roots that are rational numbers. To remind you, what is a rational number? A rational number is in the form of a over b, where a and b are integers. What are integers? 0, 1, 2, 3 forever. Also, negative 1, negative 2, negative 3, negative 4 forever. Those are integers. That is, a rational number can always be written in the form of one integer divided by another integer, so long as you're not dividing by 0. You can't ever divide by 0. A rational number is one integer divided by another integer, or at least it can be written that way. One integer divided by another integer, where, okay, and the denominator is not 0. So rational roots will be numbers like 3 over 2, negative 7 over 3, 4 over 5, negative 7 over 6. These are rational numbers, and they would be rational roots if they made a polynomial equal 0. For example, x squared minus 4, the rational roots would be 2 over 1 and negative 2 over 1. That is, these are rational numbers. That is, 2 and negative 2 are rational numbers, because I can write it as one integer divided by another integer. And none of those, and the bottom number was not 0. I can write negative 2 as an integer divided by another integer, and that integer I'm dividing by is not 0. Okay. So 7 is rational, negative 4 is rational, 13 is rational. Why? Because you can think of them as over 1. In fact, 13, you can think of 26 over 2, or 39 over 3. And both of these fractions really equal 13, and the top numbers are integers, and the bottom numbers are integers, and the bottom numbers are not 0. Okay. Now that we know what a rational root is, it's a fraction, it's a rational number that's a root of our function. It's a 0. It makes it 0. Roots and zeros are the same. Now, the rational root theorem is a method to generate all the possible rational zeros. That is, we will find a list of rational numbers. Most of them will probably not be zeros. But if there are any rational zeros, they will be in our list. our list contains all irrational zeros and then some that are not. It may contain some that are not. Usually it will. Okay, so how do we do this? Find the possible rational zeros or rational roots for the following. For 3x squared minus 4x plus 6. And the way you do it is you find numbers that go into 6. The numbers that go into 6, the numbers that go into positive 6 are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. They all go evenly into 6. Do that. Do what we just did to the constant. Then go to the term that has the highest power of x. Not always just the first one. In this case, it's the first one. You have 3. Write down the numbers that go into 3. Plus minus 1 goes into 3, and plus minus 3 goes into 3. Now, we want to form all the possible fractions we can, where this is 8 numbers. There are 8 numbers here, and there are 4 numbers here. We want to form all possible fractions where we want to form all possible fractions that have one of those 8 numbers on top in the numerator and one of these 4 numbers in the bottom. For example, 1 by 1, I'll take the top numbers and I'll divide by plus minus 1. And I'll get 1 divided by plus minus 1 divided by plus minus 1 is plus minus 1. Plus minus 2 divided by plus minus 1 is plus minus 2. Plus minus 3 divided by plus minus 1 is 3. Positive 6, or plus minus 6 divided by plus minus 1 is plus minus 6. So I divided all the top numbers by plus minus 1. Now I'm going to continue by dividing the top numbers by plus minus 3. So I take plus minus 1 and I divide by plus minus 3, and the answer I get will be plus minus 1/3. You get plus minus 1/3. You take the plus minus 2 and divide it by 3. So you get plus minus 2/3. You take the plus minus 3 divided by plus minus 3. You get plus minus 1, which I already wrote. I don't have to write it again. Then you take plus minus 6 divided by plus minus 3. And again, coincidentally, you get an answer that's already there. These 3, 4, 5, these 12 numbers are the only possible rational zeros for this equation here. Okay, those are the only possible numbers. That is, no way will 7 over 5, which is not on this list. 7 over 5 is not on the list. No way will 7 over 5, x being 7 over 5, it'll never make that equation 0. This equation will not be 0 at 7 over 5. Okay? Now, plus 6, maybe. Minus 6, maybe. Plus or minus 1/3, maybe. But if it's not on that list, for example, 7 over 51 is not on that list, no way will 7 over 51 make that 0. Does it mean that their numbers in the box are the only zeros? Only possible zeros? Notice I didn't say rational zeros. The answer is no. It might be that 2 minus the square root of 5 over 7 is a 0. It might be. But 2 minus square root of 5 over 7 is not a rational number. Okay, I want you to realize that there might be other zeros. Okay, let's try a different one. Here we just want to list the possible rational zeros. List the possible rational zeros. Okay, if you have 3x squared minus 6x to the 5th plus 2x minus 8. Well, what are the possible rational zeros for this equation? Well, find the constant, negative 8. The numbers that go into negative 8 evenly, the integers I should say, are plus or minus 1, plus and minus 2, plus and minus 4 go into 8, and plus and minus 8 go into 8. Then you find a number in front of the largest term. The term that has the highest power is what I mean to say. And the number in front is negative 6. Doesn't even matter if you write 6 or negative 6, because the same numbers that go into negative 6 also go into 6. Okay, what goes into negative 6? Plus minus 1, plus minus 2, plus minus 3, plus minus 6. To convince you of this, say this, negative 2. Negative 2 goes into 6. Negative 6 goes in 3 times. Even 2. 2 goes into negative 6 evenly. Negative 3 times. The numbers that I'm writing down, they all go into 6. Above that line, they all go into 8 or negative 8. Okay, now we need to form all the possible fractions where we use one of these numbers on top, there's 8 of them, and coincident, and the denominator, we use one of those numbers in the bottom, which happen to be 8 numbers. What are the 8 numbers on top? 1, negative 1, 2, negative 2, 4, negative 4, 8, negative 8. Plus minus 8 is 2 numbers. It's positive 8 and it's negative 8. Okay, now let's be more careful. So we're going to take plus minus 1 and divide by plus minus 1. That is, we have positive 1 or negative 1 that we can put on the top, and on the bottom, plus 1 or minus 1. We can get 4 fractions. I can put plus 1 on top and plus 1 on the bottom. Or I can put plus 1 on top and minus 1 on the bottom. Or I could use negative 1 for the top. Negative 1 on the top, or plus 1 on the bottom, or negative 1 on the top, and negative 1 on the bottom. These fractions, plus 1 over plus 1 is plus 1. This fraction is negative 1. This fraction is also negative 1. This fraction is positive 1. That is, I only get back plus minus 1. If I do 4 in this 3, I can have plus 4 with 3 in the bottom. I can have plus 4 with negative 3 in the bottom. I can have negative 4 with plus 3 on the bottom, or negative 3 on the bottom. The thing is that this is positive 4/3, and so is that. So we get plus 4/3, and both of these are minus 4/3. We get plus or minus 4/3. So we can just always say plus minus and then do the division. So now, as requested, let us list the rational zeros, the possible rational zeros. Okay, so I'm going to divide every number by plus minus 1. Every number on top. So you just get the top numbers. Plus minus 1, plus minus 2, plus minus 4, plus minus 8. Now I'm going to take every number on top and divide by 2. But I always get plus minus. I get 1 over 2, and then I get 2 over 2. 2 over 2. But I already have that. That's 1. Then I get 4 over 2, which I happen to already have. And then I get 8 over the 2, which I already have right there. So I'm done with the 1 and the 2. Now I divide all the top numbers by 3. So I get plus minus 1/3, plus minus 2/3, plus minus 4/3, and then plus minus 8/3. So now I'm done with the 3. Now I divide all the top numbers by plus minus 6. And I get first 1 divided by 6, and then I get 2 divided by 6, which is a third. Then I divide the 4 by the 6, which is 2/3 I already have. Then I divide 8 by 6, which is 4/3, which I already have. So here is the list of possible rational zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 times 2. Because each of those were 2 numbers. There are 20 possible zeros. There are 20 possible zeros. Okay, so now let's try to figure out how to find the zeros. Not just find the possible ones. Let's find the zeros. Excuse me one moment, please. Suppose you have x cubed minus 2x squared minus 1x plus 2. And the question is to find the zeros, to find them. Now, before we do that, let's see what it means. First of all, let's just call it something. Let's call it f of x. Now, what would it mean to find a zero? If a, the number a is a 0, that means f of a equals 0. That is, when you plug it in here, when you plug in the number a, you get 0. But wait a minute. I know how to find f of a number. I put the number in front, I put whatever I put here, and then I look for my remainder. My remainder will be f of a. Now, if f of a is 0, then a is a root. In fact, that's the only time. If a is a root, what if I go the other way? If a is a root, then isn't f of a equals 0? The answer is yes. If something's a root, then f of it will be 0. What goes in the middle here is the phrase if and only if. That means is the same as. Is the same as. These two statements are the same. Those two statements are the same. So if I want to see, if I have a value, remember I list the possible rational roots? They're possible. How do I know if it's a root? Well, if it's a root, if f of a is 0. And how do I tell if f of a is 0? I use synthetic division, and I look for the remainder. Okay. We understood that. That's pretty good. But how can we get a little bit more mechanical about it? The instructions are to find the zeros of f of x. So what you want to do is list the possible rational zeros or roots. So we want numbers that go into the constant, Numbers that go into 2 are plus minus 1 and plus minus 2. And it's understood as 1x cubed is their leading term. The leading term doesn't have to be the first term. It's a term with the highest power. The numbers that go into 1 are just plus minus 1. So the possible zeros will be plus minus 1 divided by plus minus 1, which is plus minus 1, as well as plus minus 2 divided by plus minus 1, which is plus minus 2. Here are the 4 possible zeros. Okay, now I can, 1, negative 1, 2, and negative 2. I can take one by one. This is not so off the wall. I can take one by one and plug them in for x. Or I can use synthetic division with 1 on the outside. The top line, the top equation, is 1x cubed, negative 2x squares, negative 1x's. The constant is 2. 1 plus 0 is 1. Multiply, bring it up there. Add, get negative 1. Multiply, bring it up there. Add, get negative 2. Multiply, put the answer up here. And here is the remainder, which is 0. So I didn't know it would work, but it turns out that 1 is a 0. So we have 1. It worked. Now, since it's a cubic, there might be 3 zeros. We can try one other. Let's try negative 1. Negative 1, 1, negative 2, negative 1, 2. These numbers will not change unless you change the polynomial. You add, you multiply by negative 1, you add, you multiply by negative 1, you get 3. You add, you get 2. Look at this. You multiply by negative 1 by 2, you get negative 2. And when you add, you get 0. So it turns out that negative 1 is also a 0. Now, complex numbers, non-rational roots, come in pairs. Well, there's only 3 possible zeros. There's 3 zeros, and we found 2 of them. And they weren't non-rational. There cannot be one non-rational root. Non-rational roots, whether they're complex roots or real roots, they come in pairs. But our polynomial can only have 3. So if it has 2 rational zeros, then it has to have a third. That is, 2 or negative 2 will make this 0. But if you didn't understand that, well then you test all the possible zeros. Let's try 2. 2. You have 2. Like I said, this list of numbers will not change. 1 plus 0 is 1. 2 times 1 is 2. You add, you get 0. 2 times 0 is 0. You add, you get negative 1. 2 times negative 1 is negative 2. You add, you don't get 0. That is, 2 is not a rational 0 or a rational root. Well, we'll see if I lied. I promised 3 of them would work. So on an exam, if you're running out of time, you can say negative 2 must be the other rational root. Okay, let's try it. Negative 2, and then these sets of numbers. 1, negative 2, negative 1, 2. 1 plus 0 is 1. You multiply, the answer goes there. You add, you multiply, the answer goes there. You add, And when you multiply, the answer goes there. And then you add, you get negative 12, which is not 0. Okay, something went wrong with 2. 2 should have worked. 8 minus 8. 2 should have worked. Let's try 2 again. I'm sorry that something went wrong. 2. We have 1x cubed, negative 2x squares, negative 1x's, and then plus 2. I add these, I get 1. 2 times 1 is 2. I add these, I get 0. 2 times 0 is 0. And when I add, I get negative 1. And 2 times negative 1 is negative 2. And we get 0. All of you were laughing because you caught the error as I made it. Okay, so it turns out that 2 worked and negative 2 didn't work. You can only have 3 zeros. And we found them. So the instructions were to find the 3 zeros, and step 1 was to list them. Step 1 was to list them, and then below this line, the testing was done. Down here, we did the testing. I erased some of them, but we tested 1 and it worked. We tested negative 1 and it worked. We tested 2 and eventually it worked. And we even tested negative 2 and it didn't work. But that would be how you could find the zeros. But now, what if you say have a cubic, but what? You have a cubic, but not all the zeros are rational. That is, suppose you have x cubed, minus x squared minus 5x plus 5. Suppose you have that. And the instructions are to find all 3 zeros. Find all 3 zeros. Or at least convince us all 3 real zeros. Or convince us that there aren't 3 zeros. Say there's 2 zeros, 2 real zeros, which you have to show me, and 1 imaginary. Or there's 1 real zero and 2 imaginaries. Remember, imaginaries come in pairs. Real zeros that are not rational. That is things like 3 plus the square root of 5 over 2. They will also have 3 minus square root of 5 over 2 as a zero. They come in pairs. Rational zeros, they don't have to come in pairs. Okay, so nonetheless, find the numbers that go into 5, which are just plus minus 1 and plus minus 5, and find the numbers that go into that understood 1, which are just plus minus 1. So the possible zeros are plus minus 1, plus minus 5. Those are the set of possible rational zeros. That is 1, negative 1, 5, negative 5. Let's try some of them. Let's try 1. 1. Sorry. Our beginning polynomial, this one up here, it has 1x cubed, negative 1x squared, negative 5x's, plus 5. Okay. I like to put a 0 here. I add, I get 1. I multiply, I get 1. I add, I get 0. I multiply, I get 0. I add, I get negative 5. I multiply, I get negative 5. And I add, and my remainder is 0. So 1 is a 0. X equal 1 is a 0. Now, let's understand what this means. Here's a very, very important concept that you need to see this very clearly. For example, if I told you that what's in that bracket, and this statement is probably wrong, but if I told you what's in this bracket is equal to x plus 2 times x minus 7. If I ask you, what will this be when x is 10? Well, it'd be a lot easier to plug 10 in here. 10 plus 2 is 12. 10 minus 7 is 5. The answer is 60. Assuming they were equal, trust me, when you plug in 10 on the right, which is a lot harder, you would get the same answer, 60. If they were equal, make believe they were. Okay. If the left side equals the right side, always, then no matter what x you plug in, you get the same answer. Like x squared minus 4, this is x plus 2 times x minus 2. If x is 10, for example, 10 squared is 100. 100 minus 4, that's 96. 10 plus 2 is 8. I meant to say 10 plus 2 is 12. And 10 minus 2 is 8. And you know what? When you multiply 12 times 8, you get the same answer. That's because this and that are equal. Now, we just learned that when we plug 1 into that bottom left equation, let me erase this because it has nothing to do with the problem. We just learned that when you plug 1 in, your remainder is 0. That is, 1 is a factor. 1 makes the top 0. Well, I claim if 1 makes the top 0, if I plug in 1 for x and I get 0, let's suppose when I factor it, I get many different factors. And each one, all I can tell you is, it's not x minus 1, it's x minus a different number. It's not x minus 1, it's x minus a different number, or x plus a different number. It's not x minus 1. It's not 1 there. Well then, if this is x minus not 1, and then I multiply it by x minus other than 1, and I multiply by x minus not 1, other than 1, well, you know what? When I plug 1 in for x, I won't get 0. Because if x is 1, and you take away not 1, you take away 2, you take away 7, you take away negative 9, this will not be 0. And if I plug 1 in for x, and I don't take away 1, I won't get 0. If I plug in 1 for x right here, and I don't take away 1, I won't get 0. When I multiply all of these, when I multiply, I won't get 0. But wait a minute. This bottom, when I plug in 1, is not 0. But when I plug 1 in the right side, it is 0. After all, 1 cubed is 1, minus 1 squared is 1, that's 0. Minus 5 times 1 is minus 5, plus 5 is 0. When I plug 1 in, I'm supposed to get 0. What I'm getting at is, we were mistaken. When we said that x minus 1 is not a factor, we were mistaken. We were mistaken. One of the factors is x minus 1. Now, let's just look at this. This is heavy duty, but let's look at something. you have x cubed minus x squared minus 5x plus 5. And you were asked to divide by x minus 1. Wouldn't you have done this? Wouldn't you have done this? The answer is yes. And the answer would be remainder, which is 0, so no remainder, constant x and x squared. Wouldn't the answer be 1x squared plus 0x's, which I won't write, minus 5? And I thought that wasn't there. Okay. That's what we really did when we did the synthetic division. That's what we did. Well, I'm very big on the next statement I'm going to say. This, the bottom, times the other side of the equal sign equals the top. That is, we know that x cubed minus x squared minus 5x plus 5 is equal to x minus 1 times x squared minus 5. Okay, so we've come a long way. We just realized that. And we'll do a couple more, make sure we understand this nicely. We now reach that. We now know this. Now I'd like to factor some more. X cubed minus x squared minus 5x plus 5. This is equal to x minus 1 times what? Can we factor x squared minus 5? And the answer is yes. A lot of people say, no, we can't. But that's not true. There's something squared that gives you 5. And you need to know that like you know your name. The square root of 5. So I can factor this. I have x being squared here. I have square root of 5 being squared there. And I must have a minus in the middle. Oh, I write down in the first bracket what I'm squaring. I write down in the second bracket what I'm squaring. One bracket a minus, the other is a plus. That's how you factor x squared minus 5. So, let me just write it on the line below. We know that this, which I wrote down there, is equal to x minus 1 times x squared minus 5. But x squared minus 5 can be written this way. Now that we have linear factors, we can say what the zeros are. What are the zeros? What are the roots? Well, what makes this 0 is x being 1. What makes this 0 is x being square root of 5. And what makes that 0 is negative square root of 5. Okay, those are the 3 zeros. Notice that square root of 5 is irrational. But it's also the same as 0 plus square root of 5. And the other answer was 0 minus square root of 5, which is negative square root of 5. So they did the real roots that were non-rational came in pairs. Square root of 5 minus square root of 5. Okay, those are the 3 answers. Okay, one needs to study this more than most sections in pre-calc. Then again, I've always felt this was the hardest part, and my students said that I don't know what I'm talking about, that this was pretty easy. So hopefully it's easy for you. Suppose you wanted to find the zeros of this. Suppose you were asked to find the zeros of this. Suppose you had x cubed minus 3x squared minus 4x plus 12. How can you find the zeros of this? You know, I wouldn't suggests that you don't try like 1 and minus 1. They're pretty quick. When you plug in 1, you'll get 1 minus 3 minus 4 plus 12. Because the x's don't do anything. 4 times 1 is 4. 1 squared is 1, and 3 times 1 is 3. 1 cubed is still 1. But it turns out that's not 0. Okay, so it didn't work too well. But it only takes a second. So we find numbers that go into the constant. Numbers that go into 12 are plus minus 1, plus minus 2, and 3, and 4, and 6, and 12. Yes. And the numbers that go into the coefficient of the x cubed being the highest power of x, is 1. The numbers that go into 1 are just plus minus 1. So you divide all these numbers that I just circled by plus minus 1, and you get the same numbers I just circled. Those are the possible rational zeros or roots. There are 12 of them. And we know it's not 1, we tried it. But if you can try 1, you have 1x cubed minus 3x squared minus 4x is plus 12. Times this number by 1, it's 1. Add, times it by 1, it stays the same. Add, times it by 1, you don't get 0. So 1 is not or 0. Let's try negative 1 with these same numbers. 1, negative 3, negative 4, 12. When you multiply by 1, you just change the sign. Change the sign of 1, get negative 1. Add, get negative 4. Multiply by negative 1, that is, change the sign. You get 4, you add. Negative 1 times 0 is 0, it goes there. And the remainder is 12, which again is not 0. And now, 0 is done. It's not 0. I meant to say it's not 1 or minus 1. Okay, let's try plus minus 2. Let's try 2. 0. 1 plus 0 is 1. Times it by 2. Goes up there. Add, get negative 1. Times it by 2. Add, get negative 6. Times it by 2. You add, you get 0. Okay. Now, this tells us that the top line, x cubed minus 3x squared minus 4x plus 12, is equal to x minus this number. X minus 2 must be a factor. The other factor comes from right here. 1x squared minus x. 1x squared minus 1x minus 6. Now, the problem says to find the zeros. You can try to factor this to find the zeros. You can use the quadratic formula to find the zeros. You can complete the square to find the zeros. Or you can continue with this list right here. We tried 2. Negative 2 plus minus 3 plus minus 4 plus minus 6 plus minus 12. But I think the easiest way is to say try to factor it. Let's try to factor it. Since it's x squared and not 3x squared, it's x squared, we'll try to factor it with x followed by a number times x followed by another number. And the two numbers should multiply out to negative 6, but add up to the number in front of x. Two numbers that multiply out to negative 6, but add up to negative 1, are negative 3 and positive 2. So, we have x minus 2 that's in front, right here, times x squared minus x minus 6, which is x minus 3 times x plus 2. Now we can find the zeros, because they're all linear factors. 2, 3, negative 2. Now what happens is, if you don't see the factors of x squared minus x minus 6, you might have to resort to the formula. Now just for the record, we just came up with 3 and negative 2. And what do you know? They were on our possible list. Plus 3 and negative 2. They were on our list because they're rational. Every rational number is on, every rational 0 is on this list. Unfortunately, there's lots that aren't. Plus minus 4 wasn't a 0. Plus minus 6 weren't a 0. Plus minus 12 wasn't a 0. They're only possible zeros. So the synthetic division kind of helps us out a lot. We don't have to do long division. How would you show that a polynomial does not have any rational zeros? How would you show that polynomial does not have any zeros? Well, one way would be to find the 3 zeros and say, look, none of them are rational. But the easiest way is, in this case, since the numbers are small, are to list the possible rational zeros and show that none of them work. For example, numbers that go into negative 2 are plus 1, plus minus 1, and plus minus 2. Numbers that go into 1 are just plus minus 1. And when you divide the 4 numbers on top by the 2 numbers on the bottom, the only possible fractions you get are plus minus 1 and plus minus 2. There are only 4 fractions that you can write where you put, one might say 8 fractions. For example, you can have plus 1 on top, where plus 1 on the bottom, or minus 1 on the bottom. You can have the numerator being minus 1 with plus 1 on the bottom, or minus 1 on the bottom. You can have the numerator have plus 2 with plus 1 on the bottom, or minus 1 on the bottom. Or you can have negative 2 on top, where plus 1 on the bottom, or negative 1 on the bottom. The bottom line is, sometimes you get plus 1, sometimes you get negative 1. These are repeats. Negative 1, plus 1. You get plus or minus 1. Here, you get plus 2. Over here, you get plus 2. These two give you negative 2. Negative 2. You get plus minus 1 or plus minus 2. Exactly what I said. Those are the only possible rational zeros. Okay, so we test all 4 of them and we say, look, none of them worked. There are no rational zeros. If none of the possible ones actually work, well then there are none. Okay, so let's show that. 1. I'm going to try plus 1. 1x cubed, no x squares, negative 1 x's, constants negative 2. I try it with 1, I'll try it with negative 1, and then due to lack of board space, I'll erase, and then I'll try it with 2 and negative 2. 1 multiplied by 1 is 1, add get 1, multiply by 1 get 1, add get 0, multiply by 1, it's still 0, and you get negative 2 for the remainder, which is not 0. So 1 did not work. Let's try negative 1. This number times negative 1 is negative 1. Add. This number times negative 1 is plus 1. Add. Negative 1 times 0 is 0. You add. You get negative 2, which is not 0. And maybe we do have enough space to do all 4 without erasing. Let's try 2. 1, 0, negative 1, negative 2. 1 plus 0 is 1, times the 2 in front is 2. Add, get 2. Multiply by 2, get 4. You add these, you get 3. You multiply by 2, you get 4, which is not 0. 2 is not a 0. Now what about negative 2? Negative 2, 1, 0, negative 1, negative 2. 1 plus 0 is 1, times it by negative 2, add negative 2, times it by the negative 2 in front, which is 4, add, get 3, multiply it by the negative 2 in front, get negative 6, and regardless of what those numbers add up to, it's not the number 0. So, none of them were zeros. How did we prove it? We found the list of the possible rational zeros, and we showed that none of them worked. Okay. One of the things you have to remember is that theorem. If a is a 0, then x minus a must be a factor. Okay. A is a root is the same as x minus a. X minus a is a factor. Again, if you have some mess, if you have 3x cubed minus 4x squared plus 5x minus 6, and I tell you that when you plug a in, out comes 0. Well, one of these factors must be, whether there's 3 of them or 4 of them or just one of them or 50. If none of them are x minus a, it's x minus different than a, x minus something other than a, x minus not a, x minus not a. Well, like I'm saying, when I plug a in here, I get 0. But if you plug a in here, if you have a and you take away a, you get 0. But if you have a and you're not taking away a, then all I can say is you don't have 0. Times, if x is a and you're not taking away a, oh, you're not getting 0. You're not getting 0. You're not getting 0. So 0 is equal to not 0. If you keep multiplying numbers that are not 0, you don't get 0. Oh, we must have been mistaken. I'm so sorry. One of the factors must be x minus a. I thought maybe I was wrong, but I was wrong. One of the factors must be x minus a. And if it is, then when x is a minus a is 0. So we don't get not 0 anymore, we get 0. If a is a root, then x minus a must be a factor. If x minus a is a factor, then a must be our root. They come in pairs. They come in pairs. Okay. So the next problem should be very routine as long as you understand this theorem that remains on top. A is a root is the same as x minus a is a factor. Okay, so find a polynomial with x equals 2, x equals 3, and x equals 4 as its only roots. What's the polynomial? Well, just call it a name, p of x. Well, if 2 is a 0 or a root, then x minus 2 must be one of the factors. If 3 is a root, then x minus 3 must be a factor. Let's change this to negative 4. If x equals negative 4 is a root, then x minus negative 4 must be a factor. This, of course, is x plus 4. And there's your answer. Here is a polynomial that has 2, 3, and negative 4 as its roots. You can clean it up, like multiply it out. X minus 2 times x minus 3. Well, it's x squared. If you add the two constants, negative 2 and negative 3, that's negative 5. That's how many x's you have. And if you multiply the two constants, that's the constant, plus 6. And then you need to multiply by x plus 4. Well, x squared times x is x cubed. X squared times 4 is 4x squared. Negative 5 times x is negative 5x squared. Negative 5 times 4 is negative 20x. Now the 6. 6 times x is plus 6x. Positive 6 times positive 4 is positive 24. Minus some silly arithmetic error. We get x cubed. 4 minus 5 is negative 1. Minus x squared. Negative 20 plus 6 is negative 14x's plus 24. The last line is a polynomial that has 2, 3, and negative 4 as its zeros. Now, if you wanted to check it, you can check 2. Flip 2 down and then put the coefficients. 1x cubed, negative 1x squared, negative 14x's, plus 24 the constant. 1 plus 0 is 1, times it by 2, put it here. Add, times by 2, put it there. Add, times by 2, put it there. And what do you add, and what do you know? You get 0. And you can try it with 3 and negative 4, and it should work. So finding a polynomial with zeros, pretty straightforward. Now, when I say find the polynomial with x equals those numbers as its only roots, I should have said and of degree 3. And if you look at our answer on the bottom, it is of degree 3. So what if I give you 3 zeros again, but I tell you I want you to find the polynomial with those 3 zeros, but it's of degree 5. It's of degree 5. Now, I want to also comment about that last problem. I think the zeros were 2, 3, and negative 4. So you can have x minus 2 times x minus 3 times x minus negative 4, which is x plus 4. That can be one answer. You multiply it out, you get what we got a moment ago. But you can also times it by 3. Not that 3. I mean, you can times it by 13. Still, p of 2 will be 13 times 2 minus 2 times 2 minus 3 times 2 plus 4. But you know what? That's 0. 13 times 0 times whatever, that's 0. It is putting the 13 in isn't going to do anything. Let's find p of 3. Before, we just had x minus 2 times x minus 3 times x plus 4. But putting a 13 in front isn't going to affect it. It's still going to be 0 because you got 13 times 1 times 0 times 7. That's 0. This piece is going to be 0. This piece is going to be 0 whether you put the 13 in front or not. And putting the 13 in front is not going to change it. So if you actually multiplied this out, or if another student in your class multiplied it out, their polynomial would look different than yours, because theirs is just 13 times yours. Okay. So what I'm getting at is, say for example, if you do this correctly, this is a problem in your book, and you do it correctly, when you look at the back of the book for the answer, it may not match yours. And that's no big deal. It'll just be off by a multiple. And now, in this new problem that I'm going to ask you, it won't even be off by a multiple. Students can get drastically different answers. Suppose x equals 2, x equals 5, and x equals 1 are roots. Suppose x equals 2, x equals 5, x equals 1 are roots of a polynomial of degree 5. And coincidentally, that's 5, of degree 5. Well, basically, your polynomial must have x minus 2 as a factor. It must have x minus 5 as a factor. And it must have x minus 1 as a factor. The only problem is if you multiply this out, it would be a cubic. All you need to do is put powers down in those locations, put numbers down that add up to 5. Like 2, 2, and an understood 1. That's one answer. If you squared x minus 2, and then multiply that by x minus 5, and then hold on to that last result, square x minus 1, and multiply what you had here by x minus 1 squared, that will get you the answer. Another answer, I'll call this P1. I don't want to call them all P of x's because they're not equal. I put 2 because it's the second one. It must have these bases, x minus 2, x minus 5, and x minus 1, and nothing more. But it can have them repeated. It can have x minus 5 repeated 3 times. Is it understood 1 here and understood 1 here? These powers add up to 5. You can have a third polynomial. X minus 2, x minus 5, x minus 1. You can have, and none of these powers can be 0. Because if you have x minus 1 to the 0, then this is just 1. 1 is not a 0 anymore. 1 minus 2 is not 0. 1 minus 5 is not 0. And 1 is not 0. You multiply them together, you don't get 0. You must have at least one factor of x minus 2, x minus 5, x minus 1. And here, in this case, we have 3 factors of x minus 5. That is, this is really x minus 2 times x minus 5 3 times x minus 1. The only numbers that will make this 0 is 2, 5, I already said 5, or 1. In this third example, the powers have to add up to 5. You can have 1, 1, 3. anything that adds up to 5. As long as these are positive integers, that means they can't be less than 1. Positive integers start at 1, and they add up to 5. And of course, in each of these 3 cases, you should work it out. You should square x minus 2, you should square x minus 1, and then whatever you got from squaring x minus 2, multiply that by x minus 5, and then multiply that by what you got after you calculated x minus 2 squared. To calculate P2 of x, first cube x minus 5. Take x minus 2, multiply it by whatever you got for x minus 5 cubed. That whole answer you just got, multiply it by x minus 1. The last one, first compute x minus 1 cubed. Then take x minus 2, multiply by x minus 5. Whatever answer you get, namely x squared minus 7x plus 10. Now you multiply that by x minus 1 cubed, which I think is x cubed minus 3x squared plus 3x minus 1. In fact, I'm positive. So you'd multiply this by that, and you would get your answer. But that's not the exercise here. The exercise here is to know that you must have x minus 2, because 2 is a factor. I meant to say a root. You must have x minus 5, because 5 is a root. And you must have x minus 1, because 1 is a root. And the powers have to be at least 1 and multiply out the 5. And you can multiply by whatever number you like in front, like negative 3 or 8. Of course you don't want to do that. Then you have to do an additional calculation. It's hard enough to calculate this. You don't want to now multiply by negative 3. With one exception. If your teacher says, find 3 polynomials of degree 5. Okay? If you were asked to find 3 polynomials of degree 5. Okay? You don't want to compute what's in this box and then come and compute another mess like this. You only want to compute one of these big messes in the box. In fact, you prefer to do none of them. So, for example, if after you computed what was in this box and make believe you got 3x to the 5th minus 2x plus 11. That would have taken you a long, long time to calculate. Well, there's one answer. The teacher asked you for 3 answers. Well, take this answer and multiply it by 2. You'll get 6x to the 5th minus 4x plus 22. It came fairly easily. What's another one? Multiply by negative 1. You'll get negative 3x to the 5th. 11. 2. We and calculate. We did believe we got 3x to the 5th minus 2x plus 11, and then we double on. Find any of them should be root half 5 degree. More enough both forever same. Fine. suppose the roots are x equals 2, x equals -3, x equals 7. Okay, and that's it. The roots of a fifth degree polynomial are x equals 2, x equals -3, and x equals 7. And x equals 7. The roots of a fifth degree polynomial are those three numbers. The question is, write down a possible polynomial. Write down a possible polynomial for above. Write down a possible polynomial from the information above. Well, p of x, if one root of 0 is a 2, we have x minus 2 as one factor. We have x minus -3 as another factor, which becomes x plus 3. And the third factor is x minus 7. But those are only 3. We need 5 because the degree is 5. Well, repeat some of them. That is, you can write down x minus 2 again and say x plus 3 again. Well, 1, 2, 3, 4, 5. That will give you x to the fifth. But yet only 2, -3, and 7 will make it 0. That is, you still have just these same 3 bases, but now we have 2 factors of x minus 2, we have 2 factors of x plus 3, and 1 factor of x minus 7. Okay, basically, just multiply this together. Probably the easiest way, if you remember that a squared times b squared is the same as just multiplying a and b and then squaring it. Here's a squared times b squared. I could just multiply x plus 2 by I can multiply x minus 2 by x plus 3 and get x squared plus x minus 6 and then square that. And then multiply that by x minus 7. Maybe that's easier, who knows. And you would just continue and you get what you get. First I would square x squared plus x minus 6, and whatever I get, I'll multiply by x minus 7. And that would be of the degree 5. Because at some point, when you're squaring these two, you will get x to the 4th. And then when you multiply that by x minus 7, this is going to have an x to the 4th. And when you multiply it by x, it'll give you x to the 5th. The highest power will be 5. Okay, so there's a polynomial of degree 5 that will have the desired zeros. And once again, you can put any number you want in front, like square root of 7. Okay, why you would do that? I don't know, but you can. Square root of 7. Okay, that finishes this section.